Good afternoon. Thank you for coming. I'm glad to see everybody here online. I'm going to try to give you an overview of how we can model customer revisit prediction using deep survival analysis. Before going to the technical part, let me introduce the background of our research. Nowadays, big companies like Amazon, Alibaba, and Jingdong open their new generation of retail stores to satisfy customers mainly by connecting their online and offline experiences. In addition to that, small retail chains are beginning to apply third-party retail analytics solutions built upon Wi-Fi fingerprinting and video analytics to learn more about their customer behavior. Retail operators can receive a dashboard that contains several statistics, enable them to empirically optimize some key performance indices by rearranging their products in their store. Securing and nurturing existing customers is very important. An article from Forbes said that by securing 5% of the customers, revenue would increase up to 95%. However, for big clothing stores in Seoul, we observed that more than 70% of the visits are from first-time visitors, and most of them churn out. To prevent this phenomena, retail analytics companies wanted to further understand their customer behavior and willing to develop a solution to predict customer revisit. The prediction results can be applied to marketing strategies. If the customer is likely to revisit, merchants can invite them to their premium store. If not, they should find an aggressive way for their customers to spend their money when they're on site. Now let's move on to the perspective of applied scientists like me. Predicting customer revisit requires us to set up the regression problem in a temporal setting. The training and testing period should be split by time. In some cases, we know when the customer will revisit. For others, we do not know. We call this partial observations. These partially observed visits are also used as the latest histories of training data, but it is necessary to predict when they will revisit again. Besides, the model requires to predict new customers' revisit behavior. Therefore, in this work, we developed a customer revisit prediction framework. First, we understand patterns from customer revisit histories by neural networks. Second, we handle partial observations and predict customer revisit rates by survival analysis. For some of you who are not familiar with survival analysis, it is a branch of statistics for analyzing the expected duration of time until some events happen. In our case, the time before revisiting a store. The major difference to simple regression is that survival analysis considers censoring effect. In this example, instance A and C are left and right censored cases respectively. In the simple regression, revisit interval of those cases are not clearly known and cannot be used. However, survival analysis allows predicting the event time distribution, including the fact that a revisit event has not occurred even after a certain period of time has passed. Most approaches aim to predict either survival function, which denotes a probability that the event will occur after time t, or hazard function, a conditional probability that the event of interest will happen in next unit time, under the condition that there weren't any event until time t. In the medical domain, hazard function is also known as instantaneous risk. Then, how can you combine survival analysis and deep learning? This is how we did it. There's a customer who visited 3 times during the training period, and here's an example of training a model for her 3rd visit. Let's think for a moment. There are 3 visits, and each visit contains a sequence of customer behavior, typical sequential prediction problem. Following a trend, we use deep learning for that. And now it's getting interesting. By interpreting the output vector as a quantized Hartree function, we can make a connection to survival regression. In other words, each dimension of the output vector denotes the revisit rate of each day. In this scenario, the model is finally trained by referring to the fact that customer has not revisited for the next 120 days. The deep learning part comprises 2 modules, a lower level encoder to represent each visit, and a higher level module to understand users' histories and predict customer revisit rate. For more natural understanding, we use the output dimension of 365. Let us explain those modules one by one. The purpose of a low-level encoder is to find a representation of each visit. So the raw input can be a sequence of areas that the customer passes by. It first goes through embedding layer, bidirectional LSTM, and convolutional neural network and attention networks. Notably, we expect CNN layers to automate the manual process of grouping the areas for obtaining multi-level location semantics to generate category or gender level semantics in previous research. The area sequence representation is concatenated with user representation, then reinforced by some extra features summarizing each visit, such as temporal information and previous revisit interval length. These processes allow a low-level encoder to learn comprehensive customer behavior. Next, the high-level module uses LSTM networks by getting inputs from low-level encoders, then predict its revisit rate for the coming year. Model training is done by minimizing the loss function, which is a combination of 4 sublosses, including negative log likelihood loss and RMSE loss for revisited cases, and cross entropy loss and pairwise ranking loss for all cases. To validate our model, we use Wi-Fi fingerprinted customer mobility from 4 stores located in Seoul. For each store, 50,000 customers that had visits longer than 1 minute are randomly selected. As you can see, dozens of sensors are installed in the store, and the data is collected around 1 year. We designed 2 versions of training and testing sets by varying the training lengths to 180 and 240 days. With longer training lengths, a higher number of uncensored visits can be observed. Expected revisit rate and revisit interval are also slightly high. Statistics from partial observations, as known as the latest visit of training instances, are very interesting. Average revisit interval of those cases are super large, although their average revisit rate is similar to first-time visitors. The model is compared with several baselines. The first 3 baselines, majority, Poisson process, Hawkes process, just consider the customer arrival process, ignoring covariates. The next 2 baselines consider covariates. First one is a Cox proportional hazard model, which is well known as a semi-parametric survival analysis model. Second one is a gradient boosting tree regression model using handcrafted features from multi-level trajectories. Also, we compared our model with state-of-the-art deep survival analysis model, including Neural Survival Recommender, a multitask learning framework to predict the user action and the survival rate. Another recent model is DRSA, An autoregressive model using many-to-many LSTM networks to emit the hazard rate for each cell. According to our result, our servlet model shows a higher C-index result than the baselines for censored customers, who are checkmarked here in the below figures. Also, it shows a higher F-score value than the others on evaluating new customers. Additionally, we did some ablation studies to prove the effectiveness of each module. In conclusion, we introduced a deep survival analysis framework to discover the relation between customer revisit and their mobility by considering partial observations. We expect this model can be applied to any temporal prediction problem considering multi-level user histories. Thank you.